answer period at the very end of the webinar. So if you have any questions, please jot them down and type them into the little GoToWebinar box, and I will collect those questions, and at the very end we will have a Q&A session. Also, we are recording this webinar, so if you have any questions later on, or if you missed something or you want to reference something later on, this is being recorded and will be placed on the Irrigation Association's website in a few days. So just be aware that we are recording this webinar and you can reference it later on. So we'll go ahead and get started. The title of this webinar is the Energy and Water Efficiency Nexus, and where does irrigation fit in? We've all heard a lot about the energy and water nexus, but relatively little do we hear about how irrigation plays into that and what the benefits of irrigation are when looking at energy use and water use holistically. So before we start, I want to talk a little bit about the Irrigation Association. We are a 501c6 trade association. Our mission is to promote efficient irrigation. I've listed our strategic initiatives there. They include education, certification, standards, and government public affairs. And our goal of this webinar is to bring together experts of the industry to talk about a variety of topics and to advance the discussion and possibly even identify some solutions and some benefits that our industry, the irrigation industry, can bring to the table. So that's really the focus of this webinar, and we really appreciate everyone participating and listening in on this webinar. So I want to give a little bit of an overview about the energy and water nexus and why we chose this as a topic for the third of our 5-part webinar series. When thinking about the energy and water nexus and where irrigation fits in, this is an agricultural-focused webinar. I found this graphic, which is pretty good, and it tells a good story. So there's really 3 areas we're looking at here. It's water supply and the availability of water, so that's where the water supply and security. Energy security, ensuring that we have enough energy for the United States to continue to evolve and survive. And food security, ensuring a safe and reliable food supply. Now each one of those, water is a component of that, and each one of those needs water. So in order to have water supply and security, of course you need water. In order for energy security, you need water, and that's for the production of energy, you need water. And for food security, you need water. Now, as you know, there's a lot of trends and a lot of things that influence this nexus. That's urban water use, the increase in population, and climate change, and I'll change that to climate variability. So different rainfall coming at different times in different areas. We're seeing flooding in Colorado. We're seeing not much rain out in the East Coast right now. We're seeing a continued drought in Texas. So we're seeing a lot of weather patterns now that are not going to be the same weather patterns 5-10 years from now. So they really affect what our food security is and the water supply side, and as well as energy security. So we're going to have energy shortages because of different weather patterns and water patterns that we have throughout the United States. And so what are the incentives to ensure that we have a reliable food supply, reliable energy, and reliable water supply? And that's kind of some things we're looking at here. And then where does irrigation fit in? So the irrigation, of course, is on the food security side, but it's also on the water supply and security. And how much energy does it take to use an efficient irrigation system? So these are all kind of questions that we're looking at from the irrigation industry side. And this is the first webinar that first time we're really focusing on, as an industry, the energy side of efficient irrigation and what that means to food supply, food production, and overall water use. So the nexus, that's what we're talking about here. We're going to be sick of hearing that term, the nexus, throughout this discussion. Water uses energy. There is no question about that. To clean water, to pump water, to ensure water is available, it uses energy in order to make that happen. Energy uses water. Energy requires water in order to be produced, whether it's nuclear energy or it's biofuels or it's extracting energy, it uses water. So energy is dependent on water. Agriculture needs both. In order for agriculture to produce a sufficient amount of yield, it needs water and it needs energy. So ag is actually dependent on both. And then modern society needs all 3. for all of us to survive, in order for all of us to continue living the lives that we live, we need water, we need energy, we need agriculture. So in order for the United States to continue to move forward and progress, etc., we need all of these three things, which are interdependent on one another. Energy use in the United States. During a 5-year period of 1997 to 2002, the per capita energy use in the United States declined 1.8%. Now, per capita food-related energy use in the U.S. increased by 16.4%. So you can see why policymakers, other parties outside of the irrigation industry, and those of us within the irrigation industry are very interested in energy use, in agriculture, and that energy water nexus as it relates to U.S. agriculture. And then according to a 2005 report from the state of California, electricity used for water represents more than 90% of the total electricity used for crop production in the ag sector in California. You can see that applies mostly to field crops, but also fruit, nut trees, and vineyards. So in California especially, and in other states where you're pumping water out of the ground, like in the Central Plains Aquifer, the Ogallala, energy is key. And how they use that water is going to be increased, not only for water, the water supply side, but for energy supply side, and increased focus moving forward. So the big question that we're going to attempt to address during this webinar is, where does irrigation fit in? A nexus, we need, first of all, before we even start talking about how irrigation fits in, we need to recognize that this nexus does in fact exist, that energy and water are interdependent on one another, and ag depends on both. So we need to recognize that. Second, we need to recognize that energy is embedded in every drop of water, not only used for irrigation, but everywhere. The faucets we turn on in our homes, the water that we receive from any public utility, energy is embedded in every drop of water, so especially for irrigation. Now the big question is, does using water efficiently promote energy efficiency? And that's really the crux of the discussion that we're going to have today. And I'm pleased to have two experts weigh in on this topic. The first speaker is going to be Dr. David Zoldoske. Most of us, if not all of us in the industry, know David. He's the Director of Center for Irrigation Technology at Fresno State. He's a former president of the Irrigation Association, and we are excited to recognize David at the 2013 Irrigation Show as the Person of the Year this year. So that's a great honor for David, and couldn't have gone to a better person. Our second expert is going to be Rob Sampson. Rob is 1 year into his stint as the National Water Management Engineer at USDA NRCS. In layman's term, he's the go-to guy for everything irrigation within the Natural Resources Conservation Service at the USDA. Rob comes to us from Idaho, where he was the state engineer, and has done a great job over the past year really diving in head first, or feet first, whichever you may want to refer to it as, and really getting his fingernails dirty and looking at irrigation and how the NRCS views irrigation and how to promote irrigation and efficient irrigation throughout agricultural production in the United States. So with that said, I want to first introduce Dave Zoldoske, and I will unmute his phone right now and recognize him to give a brief presentation. So David, it's all yours.
Okay, thank you, John. Can everybody hear me, I hope, John?
Yes, you're just fine.
Okay, and then I'm going to see if I can get my PowerPoint on. So I go to show screen, is that what I'm looking at?
Yep.
And just a minute here. Excuse me for a minute while I enjoy the technology. Okay, let's see if this gets us. And let's see. I think we are good to go. I just need to hit slideshow, I guess. Okay, so can everybody see that? No?
I think we're stuck on the on a different. No.
I've got it on my screen. No? That's to attendee. No one can see your screen. Click Start Sharing. Does that work?
Yep, all set.
Okay, good. We'll go from there. Okay, so this is what I've been asked to speak on, kind of the ag, water, energy nexus here, and I want to thank the Irrigation Association for providing this venue, and hopefully we can share some ideas today. So I've got a little different graph, and I'll read it to you if you can't read it clearly, but the idea is that it's the food, energy, water nexus, and really food needs to be part of the discussion, because I think if you solve just for energy and water, you may come up with answers or policies or directions that skew the results and don't really appreciate the value of food in the equation. So I actually Googled FEW, which is, again, the food, energy, water nexus, and there's quite a bit of discussion out there under this topic, and I think it's a way to broaden the discussion and really balance the inputs and outputs in a way that I think solves for perhaps a more appropriate solution. So I don't know if you can see my cursor on the screen, but it starts out, what technologies make irrigation more water efficient? That's on the left, and obviously that's a big role of the Irrigation Association and its membership. But it's only one part of this equation. And as we move sort of left to right across the top, you know, what are the water storage options for the farmer locally? It may be on-farm reservoirs so that they can pump during off-peak. Maybe they take canal water periodically, but can use it through a drip system on demand that way. So there are some on-farm engineering options that growers need to consider as they kind of move through that. And again, moving across over here to the energy efficient water treatment technologies, there's a lot of discussion on treating water only to the need of the use. And so obviously, we don't need, in all occasions, to produce potable water. But if you look at some of the Food and Drug FDA recommendations coming down, we may have to treat it further due to concerns about potential E. coli and other organisms making their way into the marketplace. So, but I think there's an area where energy input can be managed at the appropriate level. Obviously, our watersheds, at least certainly in the West here and in California, our Sierra Nevadas are a tremendous resource for generating hydropower. And how we interconnect that demand for hydropower and for water deliveries to the farming sector are important considerations. Fortunately, most of our peak demand is in the summer for electrical use, and obviously the same is for water. However, it might be different context when we start to look to support the environment. And if you look down here, what ways of operating dams sustain the wetlands and fisheries? That's a much different question. We have indigenous salmon that we have winter run of salmon and spring run of salmons, and there's flows of water that are required in the streams to maintain that may be at odds of what the growers' demand for water is to produce food and fiber. And then water reuse. You know, that's a hot topic. Much of California ag, though, is in the non-urban areas, as you would expect, and so certainly water resources from cities' treatment are very small relative to the demand of ag in those areas. However, again, at least in California, we have a huge aquifer of brackish water, particularly in the San Joaquin Valley, that has largely gone unused, obviously, because it is brackish. But therein lies a potential resource in the future for reducing the salt levels in that brackish water and applying it directly to ag. And it might be one of those areas where the state would look at it and say, gee, if we can reduce our exports out of the Delta, which are very contentious, and leave those waters for more environmental enhancements that may be may be a priority for the state, and then have the growers locally utilize brackish water under their farmsteads and then treat that water, there could be an option for the state to help subsidize that water treatment, and it becomes a win-win for everyone in the state of California. We continue to have a robust ag economy, at the same time provide more water to the environment. Interesting enough, I think the brackish water, particularly in the San Joaquin Valley, which is the largest and most productive growing region in the country, it's my understanding it's called connate water, which is basically old seawater. The San Joaquin Valley used to be an inland sea, but at that time the salt level was much, much lower, so it has much less salt in it than the ocean does today. And it's pretty much from 1,500 feet and below, there's an enormous amount of water there that is available for some future use. So technology, treatment, perhaps even policy planning, looking at these resources in ways that have never been done before, I think really bring into play new ways at viewing sustainability and the future of agriculture. And again, my perspective is from California, and so that's my bias in this conversation. But again, you can see it's optimizing solutions and innovation. So it's really bringing all these things together so that we meet the needs of society, and quite frankly, the shifting needs of society. So to that effort, we worked with our local utility, which is Pacific Gas and Electric, to utilize our 800-acre farm here on campus as a demonstration site of new technologies that will hopefully work directly with the water energy nexus, with the idea that we're also mindful of the production and food aspect of it. So we're fortunate to have a large farm adjacent to our campus. It is really a microcosm of the San Joaquin Valley. We have every major crop grown in the San Joaquin Valley on our farm at field scale level, 20 acres, 40 acres, 60 acre fields, which are not uncommon in the area here. It allows us to create a demonstration, I don't know why this thing keeps coming up, but anyway, it allows us to create a demonstration site that is of field level that growers can both view and understand the technology, and also from industry standpoint to install technology at a level that is relative to its use across large sections of irrigated agriculture. So we've got the whole farm is actually in transition. We've got companies literally from all over the world engaged on the farm with control systems, sensing, water measurements, and really data collection is going to be real important both today and more so in the future. And what I mean by that, it's system operation. When you see flows or pressures changing, you know that the system is starting to perhaps to suffer some deterioration in its operation, and it's important that it be addressed as early as possible. Just like we would in our car, seeing that the temperature gauge is rising or the oil pressure is low, we know it's time to get it fixed before it crashes. And it's really a cooperative effort between Fresno State, industry, and government and local utilities, and it's created quite a synergy that we're very excited to be part of, and our hope is that in the future folks will be able to get on their computer like this, look at any field on the farm, look at how much water has been delivered to date, what the soil water status is, the cost of water that's been applied to that field, really the information that is important to operating today's farms. So again, as we look at the different technologies that are out there, it's pretty basic stuff, but it is amazing how few water meters are actually implemented in farming, in new irrigation systems in California. And you think that would be standard practice, but we've got two types of irrigation systems that, as my understanding, that are installed. One is the dealer simply works with an established customer and puts the best system he can in. But the other, unfortunately, is they want 3 bids and the low bidder gets it. And typically one of the first things taken out of an irrigation system is an $800 or $1,200 water meter, which means that you're flying blind at some level. And also we're seeing a whole new series of sensors coming in that are much more accurate, much cheaper, wireless, can measure nitrate levels in the water. We've got new sensors being installed actually next week that are coming out of the Silicon Valley that are you know, at a $200 price point that measure 5 different bits of information in the soil, temperature, soil moisture, you know, pH, other things. So and those are all wireless. So we're excited about how the industry is moving forward. We think information is really the key to managing your water and energy inputs, as well as making sure that your system operates as it's designed. We are under case studies. We know we've been looking at irrigation, particularly drip and micro, that are 10 and 15 years old, and growers tend to think that it's still at 85 or 90% efficiency at DU, and when in fact it's not. And there's lots of opportunity for improving our existing systems. I believe there's over 2 million acres of existing drip micro installed in California. And then by having these demonstration areas, they're perfect for the education and classroom instruction. We've had more growers go through our educational programs this year than ever before. Even in the summer months where we in the past have had a hard time getting growers to attend, we've actually been turning growers away. Seems like there's a lot of interest in taking sense data and applying it to water management sensor data, and that seems like that's a real growth area in the state, is to use better data to make better decisions. And of course, in our education process, we always engage the industry folks, because many times they are the experts on particular products and services that they provide. And again, it's a partnership between them and the university. And then, you know, finally, the interest of the utility obviously is not only to manage connected load, which is the you know, demand, but also we have with these smart meters, we have new opportunities to save additional money through demand response, where we may have short periods of time where irrigation is pumps are being asked to be turned off, otherwise pay sort of the draconian $1 a kilowatt hour for 15, 20 minutes, maybe a dozen times a summer. And what that really also tells us is these systems need to be designed such that they don't drain down during that period. So when you turn the system back on, you're filling the pipes for the next 15 minutes. So it may take a rethinking of how irrigation products and design go together to make sure that they can then be terminated for short periods of time and still operate at high efficiency, again, to reduce the peak demand at the state level so that they don't have to get into brownouts and blackouts, and that ag can continue to minimize its input costs while maximizing production. And then, of course, you know, again, the key components of all of this water energy use is we've got to maintain high distribution uniformity. As I mentioned earlier, many of these systems over the years degrade, and without having the proper sensors or measurements or observations or even physical measurements in the field, that change is not noted at the proper time. Irrigation management, you know, really is partnered with the irrigation or the energy management, and all those are driven by flow measurement and soil moisture sensing that give you the parameters to manage to. We are seeing folks that are putting technologies in wells and pumps so that they can understand when the flows and pressures change. Is it because the groundwater table is dropping, my pump bowl's wearing, and really understand what the changes are occurring, and then take the appropriate action and do it at the proper time. Don't wait until efficiencies have dropped off to 40 or 35% pumping plant efficiencies. And then all this data comes back, and then really it's having a dashboard to look at that data and make reasonable decisions, and then have data recorded not just yearly but seasonally, monthly, and then look at that data over time and, again, hopefully make better decisions. And at the bottom of all this is really minimizing the cost of water per acre foot, which is what the two elements that we started talking about, both water and energy. And so that's really where we need to end up, is to make sure that that cost is managed at its lowest optimization. And so I wanted to just add my email address to this conversation. So if you want to ask me any questions specifically, just email me, and I do promise to get back to you in a reasonable time frame. So those are my initial my comments on this webinar, and so I'll just leave that open and wait for the next speaker. Rob?
Thank you, David. Let's see here. I will now introduce Rob Sampson, who is the National Water Management Engineer with the USDA's NRCS. And Rob, let's see here, as soon as this pops up, it should be all yours. Let's see here. It's all yours.
How's that, John?
I can see your screen. There you go. Just start this presentation. You should be good to go. There you go.
John, thank you very much for the opportunity to give a little chat today, and particular thanks to Dr. Zoldoske. He set me up like a bowling pin here. After giving some of those higher level views of things, I'm going to stay with my feet firmly planted in the mud and just show you a few things that I've learned as an irrigation engineer, and some of the lessons I think my agency has learned as it puts conservation on the ground. There's some slides that are relatively general, and I'm going to blow past those very quickly. You'll get the idea. And there's several that are very specific, and I want to stop and take some time. I want to give everybody the basic tools to be able to talk about energy units as they relate to irrigation, and talk about irrigation as it relates, and thank you for this, David, to food production and the energy it takes to get that done. My contract specifies that I will always talk about NRCS's bread and butter. We help producers with planning around their natural resources, and we design and install and subsidize a significant number of irrigation systems and a wide variety of irrigation systems. I'm sure all of you are aware in the rise of low pressure pivots, and those low pressure pivots give us the ability to probably put water on in a more precise manner, but they also use quite a bit less energy. If you really want to save energy, gravity pressurize a pipeline and use the weight of the water to sprinkle irrigate. This is a project that my colleague and predecessor Bruce Sandoval is working on in Idaho, and it feeds a whole bunch of acres, but more importantly, it has enough fall that it pressurizes the sprinklers also. And that particular system, when it's completely installed, is going to have about 4,200 less horsepower than it did a couple years ago. And if you turn the kilowatt conversion, about 3,000 kilowatts, and you assume some sort of number of pumping hours and some price for electricity, it's very easy to get into the hundreds of thousands of dollars a year that this particular project won't be using anymore. That was mainly a brag just on the projects that I used to do in Idaho, because I'm finding that in Washington, D.C., I don't quite get to do as many projects like that. So traditionally, NRCS has kind of talked about irrigation efficiency this way. any water that's beneficially used, like for evapotranspiration, is divided by the amount of water that is the total amount of water that was applied to the field. And that water has losses in it going to several different places like evaporation and deep percolation. And when NRCS goes to put a new irrigation system on somebody's ground, if we think that we've improved this irrigation efficiency, we then have the tendency to report the difference between those two efficiencies as water saved. The saved water sort of implies that you can go find it somewhere. And I want to give you all a little example of some of the pitfalls, both of the term and of the concept. At a field scale, this is sort of the schematic. Again, we have this water right here, and that's divided by the sum of all the water inputs, and the red arrows specifically being losses to the system. Because you can't go find this saved water, and because increased irrigation efficiency doesn't necessarily result in water you can find somewhere, I want to show you another pitfall, and that's the pitfall of scale. Obviously, for most NRCS projects, we're looking at simply a field. And here's a horrendogram of all the different arrows of the water coming past the field and where it goes. It goes to drains. It goes below the root zone. Much of it gets used beneficially by the crop. And that's an okay calculation to do. You can sort of visualize all of those different pathways. Here it is as how NRCS envisions, or how irrigation efficiency, actually works out in the real world on a field. Assuming that this landowner has a water right for 8 units and he's got a 50% efficient system, let's simplify that and say that 4 of those units go for crop production and 4 of them go for return flow. These different colors are different considerations that play into the landowner's decision to irrigate, and that's a different discussion on a different day. But there are certain types of these constraints that NRCS at least, and probably irrigation planners in general, can influence, and there's a lot of pieces of that puzzle that they can't. So let's say we took this system from 50% efficient to 60% efficient, with the landowner still diverting their legal water right. That increase in efficiency, more often than not, we see as an increase in on-farm beneficial use. Unfortunately, in the stream or the canal or possibly the aquifer, what we've done to ourselves while taking out the same amount of water and increasing the efficiency is we have lessened the amount of water that is in the canal or the stream or possibly the aquifer. This is not what Department of Agriculture management had in mind when they set up programs, and it certainly isn't what our partner agencies such as Fish and Wildlife Service kind of expected to see, because we had been telling them about all the water we had saved. There'll be more on that here in a moment. Let's go up to a little bigger scale. So we're up around 1,000 acres now. Here's the field that we worked on before, and now we're looking at this area here, and we can do the exact same calculation of the water used divided by the total water applied. As a matter of fact, there might not even be as many parts to measure if we were going to go out and measure parts. Some of the water still runs out of the area, and some of it still moves below the roots. And maybe even by expanding the area, we get some incidental water use by non-crop species. But much of that water that runs off the farm or off the field runs to somebody else. And So while some of the water may have moved below the root zone in a particular field, it now has an opportunity to move to, say, a drain ditch and become surface water again. So our losses tend to get a little lower, making this a little smaller number and making the irrigation efficiency overall higher for that bigger scale. And we can do the same trick with a larger basin. And in general, most of the research I've found has showed that that irrigation efficiency gets to be larger. Matter of fact, that irrigation efficiency, when we're talking about it, could be 50% on an individual field, and it could be 90% basin-wide, or as you look at a larger area. That's not a very precise way to talk about water use on the land. Here's the way that NRCS would like it to work, in that we're going to raise the efficiency from 50 to 60% and change the diverted rate from 8 to about 6.7. Same amount of on-farm beneficial use, still producing the same crop. And now we have the same flow in the river before and after, and we even have a little bit extra in the stream or the canal or possibly the aquifer. But if the landowner had a legal right to 8, how excited do you think they're going to be to give up part of their legal right? Well, this is probably the reason why much of that extra water that has been freed up by better efficiencies is used for more uniform production, more crop production overall, maybe even another irrigated acre here or there. But that loss of the 1.3 units of water gives NRCS and many of the other government, mostly state, but some federal agencies, the opportunity to start to explore ways to compensate the landowner for that. Now, this is going to lead to a whole broader discussion about environmental markets, environmental services, possibly surety from persecution under the Endangered Species Act. There's a number of ways to use that water that maybe we talk the farmer out of foregoing their right on, maybe for just a little period of time. Boy, is that a longer discussion. So instead, I'm going to give you the take-homes for this first part of this discussion that we gave, we being the technical staff, gave to NRCS leadership who are still chewing on this idea. But if you don't have monetary rewards or institutional constraints or remarkably expensive water, then in general, if we improve the technology, that does increase private benefits and increases water consumption. My agency has always said that we don't do things to increase production agriculture, to which those of us who were working out in the field kind of snickered a little bit, because everybody knows that's how you sell actual projects to landowners. If they don't make a little bit more money on it or be able to farm a little bit easier, you're not going to get them to put that out on their ground. And reporting the success of irrigation projects is very difficult when you use words like irrigation efficiencies or withdrawals or water saved. They've all got problems and they've all got misnomers. But there's a lot of reasons to support irrigated agriculture, and you guys can probably guess most of these laundry lists about we can reduce energy consumption by improving efficiency. I'll get to that in a minute. Improve water quality, be able to manage the nutrients and do them much more precisely, and increase crop yields. That's important. Almost as important, however, is reducing the yield variability, because you need surety, you need protection from risk when you put that crop in the ground, that you're going to be able to get the right amount of water to it. So what kind of efficiency should we talk about if this irrigation efficiency is fraught with pitfalls? And one of the worst pitfalls being that we can't measure very well the first number that's in it. It's very hard to tell accurately exactly how much water was beneficially used. And this doesn't talk about uniformity. If we under-irrigated the whole field and got all the water into the root zone where the plant could use it, we might end up being 100% efficient, but it wouldn't probably be very good for the crop. Well, we can talk about distribution uniformity, for instance, which is a nice measure, but it's a little hard to measure also. That's about how well the water is smeared across the field and into the root zone. We can talk about water use efficiency. So you take some sort of a pounds per acre yield and maybe divide that by pounds per acre of total water that went on the field. And you can talk about an economic efficiency, and this is probably the one that most landowners think of as some sort of net profit compared to how many gallons of water were used. And as soon as water is very, very expensive, that starts to cut into the net profit, and this economic efficiency gets to be very important. In places in the West where water isn't very expensive, all I can tell you is that at some point it will be. It's a very scarce commodity, and the climate changes that are going on around us are going to impact it. Now let's get down to some tactical stuff. I just want to give you all some examples. Let's say we walked up to a pumping plant and we found out that the shaft of the electric motor was putting out 5 horsepower and that the power meter was telling us that it was consuming 4 kilowatts. Very simple conversion if we get kilowatts back to horsepower, horsepower to kilowatts, and we can tell that the ratio between those two numbers, output divided by input, is 93%. But it's a little hard to grab the spinning shaft of a electric motor and decide that was how much power got delivered to a pump. So here's another thing that we can measure. Maybe we can take the pump efficiency into account. Let's say the pump's putting out 200 gallons per minute at a pressure of about 35 psi, and we can use this conversion here to get psi into feet, because feet is what goes into our simple water horsepower equation. So we can look at the horsepower coming into the pump, that 5 horsepower, and we can calculate the water horsepower to be something a little less than that, say 4.1, and we have an 82% efficient pump. If we combine the pump efficiency and the motor efficiency, we have what's known as the wire-to-water efficiency. So we get 3/4 of the kilowatts in pressurizing water and moving it around. Of the kilowatts that we put in, we get 3/4 of them to do work. Since we can't grab the spinning shaft of a motor very easily or put a load cell on it, what you do in practice in the field is to observe the electric meter to decide what the kilowatt input is. I can't describe to you right now how to do that because there's a lot of different meters and you got to do each one a little different, but your local power company person can help you with that. Then you read the well cared for and accurate pressure gauge that is there, and the flow meter that David mentioned hopefully was installed but isn't installed on a majority of systems. I've never understood that. And then you get the output, so you can do the wire-to-water calculation quite directly if you look at the input energy divided into the output energy. If you're using an internal combustion engine, you would use some sort of a value of energy for the fuel, and you'd have to know the rate of fuel consumption. How much per hour is being burned in the engine. And the standard power plant efficiency for electric pump plant from the Nebraska pump test is about greater than 68%. The overall pumping plant efficiency for diesel is greater than about 25%, because whenever you have an internal combustion or a diesel engine, you start off with a fairly low efficiency to begin with. Here's different energy units for different fuels, and I just give you this as a reference, but I also did a calculation checking how many units you could buy with $1. And I made some assumptions about cost down here. Electricity is a really nice form of energy that will probably get more expensive as we continue to try to improve the grid and use energy in an environmentally conscious way. Okay, now let's get down to the real brass tacks. Let's save some money, because that's what motivates people. There's 3 variables you can play with in a pumped irrigation system, and the only 3 directions that they can go is you can have less flow or less pressure, or you can run the pump less time. The nice thing about those relationships is they're mostly linear. In other words, for a rough estimate, you can calculate right away how much money you might save if you change flow, pressure, or time, because they're linearly related. Pumping plant efficiency isn't quite linear related, and we want to make that a higher number. But you can still guesstimate how much you would save in energy costs if you change your pumping plant efficiency. For my money, the best 3 tricks I know are to go get really good flow meters, read them, and keep records. And to get really good pressure gauges and scatter them all over the system and read them, put a valve between the pipe and the gauge so you don't rattle the needle off the gauge. And you might want to look into a variable speed drive for your pump. They're a pretty good idea when you got lots of complicated machinery out there, or when you're irrigating a lot of different crops. They are not the solution for every problem. But if you got the right system, a variable speed drive will change how much money you have to put out. Well, what's a 10% increase in efficiency worth to you? Let's say our wire to water increases 65 to 75%. I made some swags about number of hours that the pump runs and the cost of electricity. If we were putting 4 units into our 3/4 wire to water efficiency, we were getting 3 units out, and we can simply look at that 3 units at a lower efficiency, multiply by all of the conversions that we need to get to dollars, and see that that 10% is worth about $80 a year for us. Use similar ratios on flow, time, or pressure. So for instance, if we reduce the overall head that a pump has to put out from 200 to 180, that's a 10% reduction, and you can just very quickly calculate that you'd get about a 10% reduction in energy. One caveat, if you do go messing around with flow or head, you could easily change the efficiency point on your pump, and that could contradict what you're trying to do to improve the system efficiency. So you got to make sure you're in the sweet spot of your pump curve, which is, needless to say, another discussion for another day. But you want to be in the high efficiency, and as you change your pressure or your flow, you could move to a lower efficiency for that pump. I hope I've generated some questions. I hope I've given you a few tools that you can use to think about energy and water and how carefully we have to use the terms when we're talking about efficiencies. Electric motors and centrifugal pumps make the decision pretty straightforward, make the discussion pretty straightforward, but terms like irrigation efficiency and basin efficiency need to be really well defined. And we need to admit, at least at a policy level, that a lot of the water goes to more uniform crop, more food, and that's good. So I'll leave you with the notion of more crop per drop, and energy conservation would be more power per watt hour. And thanks very much to my incredible support team, Hamid and Jerry and Bruce. I appreciate their help looking this over. And John, that's what I've got.
Great, thank you, Rob. So I remind everyone, if you have any questions, we've already gotten a few, to go ahead and type them into the question box in your GoToWebinar. In your GoToWebinar application, and we will get to those questions now. Both Dave and Rob, there's a couple questions regarding a simple, maybe not a simple, but a calculation that a third party can develop, whether it's NRCS, CIT, IA, or just a recognized calculation that the irrigation industry, dealers, designers, consultants can take to farmers, where they can look at net savings of energy related to irrigation efficiency increases. And I'll let both of you kind of take that question, and both of you kind of talked about it, and I think, Dave, it's one of the things you're looking at, and Rob, one of the things you referred to in Idaho regarding eliminating the 4,000 horsepower units, converted kilowatts. So I just wanted to kind of start out with that question for both of you. Rob, did you want to go first?
After you, David.
Oh, David, go ahead, Dave.
Okay, well, I think one of the opportunities for us as an industry is to establish basic performance standards and not base the purchase of an irrigation system on least cost. And it might include things like total dynamic head. You know, one system might be 50 horse, one might be 40. The 50 horse might use smaller pipes so that it requires more energy, but maybe that's not the life cost of the system. So I think one of the ways we should be looking at characterizing the performance of these systems is in the life cost of the system. And look, you know, obviously, as we discussed, the amount of water, the difference between the amount of water applied and the water available to the plant, and that's really back to distribution uniformity and the energy required to get there. But I think setting a standard for which then growers could go to dealers if they want to shop price and say, I want the least cost, but I want it to meet these performance standards would be one way to help the industry.
Rob, do you have any thoughts on that?
What I heard was, is there an equation or a tool that somebody could produce that would help dealers work with landowners as they made decisions?
Yes, regarding energy savings relating to water use, on-farm water use.
Okay,
and if there, yeah, go ahead.
Okay, so unfortunately, there's no way to boil that down because, and David alluded to this, they're very, very site-specific installations and site-specific analyses. NRCS has a technical note coming out on analysis of a system for variable speed drives, and we have several spreadsheet-type inventory forms to analyze what's going on now with a landowner's system. And unfortunately, I think the odds will boil it down to a couple of simple, I think I boiled it down as simple as it can get for looking at very simple systems. Because once they start to hook more and more stuff on them, they get very complicated, and you definitely want to look at them as a life cycle cost to make sure that the landowner has all the information they need to make a decision. Now, these spreadsheet tools that NRCS has, they're very handy if folks want to learn how to use them, because as the landowner says things like, well, what about if electricity cost goes up? You can simply enter it into a spreadsheet or a small computer program, and that will rearrange the analysis and help the landowner and the dealer do what-if type scenarios.
And are those NRCS calculations, spreadsheets?
Yeah,
and
are
they available to the industry, or just those who are entering into an NRCS contract?
No, for the most part, we let these go, but we let them go with huge buyer beware caveats.
Yeah.
Particularly spreadsheets. But anybody's welcome to use them. They were developed with your dollars.
Spoken like a true government employee. So the next question is, are there any studies, you guys aware of any studies that have been done related to using flow meters to monitor and manage greater irrigation efficiency, either from the academic side, Dave, or the government side, Rob?
Well,
yes.
Go ahead, Rob.
Yeah, there have been several. I'll just stick with what I know. Idaho Water Resources Department basin efficiency calculations that were entirely based off of flow meters, and most of the Idaho water masters use flow meters to distribute the water that's being pumped. So they have a portable flow meter that they bring with them.
So if the question is really about the potential benefit, I am aware of a white paper that I read recently that indicated, I believe, a 14% savings in applied water when utilizing a water meter and a 12% reduction in energy cost. So I think there is data out there that supports that they are a good management tool for both water and energy in reducing those inputs.
Very good. And we'll have time for one more question. And before I ask that question, I want to make sure everyone knows that their email addresses are up on the screen right now. Rob gave his. You could just give it the WDC or include it. Either one would get to him. But all of our email addresses are up on the screen right now. So if I don't get to your question, I'll be sure to share these questions with the speakers, with Dave and Rob. But feel free to contact them directly as well if there's something here that I do not get. And I guess the final question is, and there's a few that popped up after this, and I apologize for not getting to it. Excuse me. Is there a general number for the improvement in wire-to-water efficiency based only on the implementation of a variable frequency drive? And it's referring to a power factor improvement. So, Rob, do you have any thoughts on that?
Yeah. Wire-to-water efficiency, there is a very good chance the power factor, you can have a leading power factor, and I'm not going to try to explain that term, but where the energy savings from an electric motor come is the fact that you don't spin it around as fast and you simply draw less energy. The power factor could be a 5% or so, but the primary thing that happens is you just don't suck up as much juice when you don't need it.
Dave, any thoughts?
No, I think it's how much water you're moving at the other end is part of that, but it's really the application that's going to provide the savings, and if you've got steady state, then VFD is not going to do you a lot of benefit. If you've got lots of variability, small plots open for planting and staggered planting and that kind of stuff, then I think there's a lot more benefits.
Very good. Well, as a reminder to everybody, I will share the rest of the questions with the panelists. I encourage you to contact them directly. Finally, I want to say thank you to both our panelists, Dave and Rob. Very good job, very informative. Our next webinar is going to be on October 17th, talking about incentives in irrigated agriculture and changing how folks irrigate through incentives. That's the website to register. I encourage everyone to look us up at the Irrigation Show. We're going to have more of these discussions on the show floor, so we look forward to that. And I appreciate everyone's attendance and participation. So thank you very much.